Hey everyone, and welcome to episode 8 of Q for Problems. Today's problem will be problem 8 from the Project Euler problem set, and we want to find the greatest product of 13 adjacent digits within this 1000 digit number. So let's have a look at the solutions. So to start off, I'm going to load in the large number from input slash pa.text. So I'm not going to count this as in the function or anything like this. I'm just going to assume that we already have the number loaded in the memory. So that is the 1000 digit number. So if I read the file, you can see I've just got it separate in lines, and then I just raise it to get a flat 1000 digit number as a string. So then to actually begin the solution one, what we want to do is take the first 13 elements, and then we want to then move on to the next 13. So we just basically move to the next part, skipping the first one because we were on that. Then we move to the next 13, then we move to the next 13, etc. So this essentially equates to creating a striated index. So I'm going to use a smaller number here just to demonstrate it. So rather than doing the 13 to start off with, we'll just start with 3 here. So if I do 3 or till 3, which would be the numbers 0, 1, 2, and then I want to plus each right. So onto those, I want to plus each of these numbers on the right, which will be till 5. So that's the numbers 0 through to 4. And if I run that, you can see what it does is it takes our 3 numbers 0, 1, 2, and it will add 0 to them. It then does 0, 1, 2 plus 1. It does 0, 1, 2 plus 2 plus 3 and plus 4. And you can see what's happening here is we're actually getting a striated index. So it's like 0, 1, 2, and then it moves on to 1, 2, 3, then it moves on to 2, 3, 4. And that's essentially for the small case. So if I want to then say, as the question give, it did 4 elements for our n. So we're going to do count of n. You can see we can get these striated indexes. So 4 of them, and this will be right up until the end. However, if I look at the very last item, you can see it actually goes slightly beyond. So we can actually just fix this with a small alteration, and that is to do neg 3 plus. So if I run that, which would be neg. So what that's actually doing is we have the count of n, which is 1000, and you can see we're going 3 elements past this because this is an index of 1000 items. It should only go up to 999, so it's actually going 3 past it, which is why we're essentially minusing 3 from this count to give us 997. So then when we do this, you can see it only goes up to 999 now. So that's allowed us to create a function, which we'll call it stride index. And essentially it will be our till second argument y plus each of the till neg, and then the rule for this neg is it's always y minus 1. So if we had been doing 6 elements here, it actually would have been neg 5 in here. And then we need to plus our x. So that gives us our striated index function. So if we run that now on, say, count n, and we do it for a stride size of 4, we can see we get the result. And then if we index that back into n, which is the numbers, we can see now we get our strings of each 4 elements. So what do we actually need to do then? We need to cast these individual characters to integers to do the product. So we don't want to actually cast this full as a number. We don't want this to be 7,316. We want it to be 7, 3, 1, and 6. So to do that, we can use the cast to long, which is following operator, and we want to do that firstly on each of these rows. However, once we do it on each of the rows, we need to do then each again on each of the individual items. So we can do that by adding another ascension each both into this. So I run that, you can see now it gives me the actual individual numbers as opposed to a full number. So if I had removed this second each both, you can see that's going to give me the numbers together rather than individually. So we'll do that. Um, so the next step then is to do the product of each of these rows. So we can do that easily just by adding a prod in here, because this is going to do prod on each of these rows anyway. So you can see that gives us all our products, and then we just want to find the max. So it'll be max. And there you have it. That is what the question actually showed. So we can turn this then into our solution one. And I'm just going to copy it across here. It's the exact same. So that's our solution one. So now if I, instead of doing 4, do 13, I can run this, find this, and then run it. And that is our solution. We can make an improvement to solution one using two ideas. So the first idea is that when we do the string, so this is what we had before, we do this row wise. We can simply just change the each right to and each left, and that'll actually do a column wise straightening. So you can see the first row of the column here was like the first row, or sorry, the first column is the same as the first row. Second column, third column, etc. So the benefit of this is that the prod function has an implicit h to do column wise built into it, so we don't actually need to include the product function within each part of our function. So we can create our C straight index um, as what we had before, but with an each right. So this will do column straighten as opposed to row straighten. So I'm just going to paste it in. So yeah, that is just what we had for the normal stride index function, but the each right is replaced with an each left. And the second idea that we can use to improve is to do, when we're doing our casting, rather than doing the casting in an each both manner, i.e. on each row, we can actually just do the casting for the whole list straight away, the 1000 numbers. So if I write out the function as we had before, so let's say count of n, and we'll just use the 4 that just they demonstrated. So that's the column straightening. And now what we want to do in front of this is have our cast as we had before, and then do it on each right of n. So this is actually casting the full list first. So it's already cast now to integers, and then we instead then do the indexing onto the straighted index with the numbers already cast, rather than doing the index first, indexing into the straighted index first, and then casting each row, which is going to be slower. So we can now have our second function. So if I actually finish this off, sorry, we can do the product then still of this, and you can see the product works. We don't need a product of each of these items. The product works over the columns. We get what we had before, and then we just want to do max. So yeah, putting that into our solution 2, I'm just going to copy it in here. So as you can see, and then if I run it for 13, we get what we had before. So we'll have a look then to see how the performance compares in our performance section. But that is an improve. It will be an improvement over S1. So our third solution involves looking at a possibility of numbers having a product of 0, and this will happen whenever there is a 0 digit involved in the product because any number multiplied by zero will give you zero. So we can check, we can split, sorry, the string, our original n, using zero and then the vs function keyword. If I run that, you can see basically it splits the 1000 digit string into um, elements by zero. So you can see the zeros themselves aren't actually included. That's okay. So what we need to do now is check these ones that have more than 13 digits, which means that anyone that has less than 13 digits before it hits a zero is going to have a zero product when we actually go to check the 13 digits. So we only need to select from this list where we have a string with more than 13 characters. And so we can do that by saying count each. And we'll assign this to a just to hold the value. So I run that, it gives me the count of each of these lists. And then I want to say where that count is greater than or equal to 13. So if I run that, that'll give me the trues or falses where it's either greater than or equal to or not. And then I just index back into A using the where keyword. So this gives me all the strings that have 13 digits or more. And then from this point, I will just do exactly what we had before. So I'm just going to copy what we had before into this. So you can see now we're running the column strided function. So this is S2 essentially. However, it's got the argument of 13 already given to it. So when I run this, on each, when I run this on each, you can see it will actually give me all the products. So it's actually doing the striding for each individual thing. So it's actually here getting the first 13, then the second 13, doing the product of all those. So you can see here there's only 13 digits in the first number, so it only corresponds to 1. However, because there's more than 13 in this second set of digits, we're actually getting all the different strided products essentially. So then what we need to do now is flatten this list to get just a single list and then just find the max element. And you can see that agrees with what we had before. So if I just copy in now the S3, move this over slightly. So this is S3 is equal to what we just had here above with just the y's instead of 13. We have y in where 13 is and x in where n is. So for performance, I'm going to just redefine our three functions here just to pass n in straight away. So we have S1, S2, S3, just for convenience. And then I'm going to run the performance test here for each of these solutions. I'm going to run it for an argument of 4, 13, 20, and 50. So this is like getting the product of all the 4 digits and all the 13 digit numbers, all the 20 digit numbers, and all the 50 digit numbers, just to show the difference whenever we're actually looking at higher digit numbers. So we can see for the number in question, for 13. So maybe I'll actually instead just select from this table and where we're looking at 13. So you can see here for 13, best time wise is actually S2. So you can see the massive improvement of S2 over S1 using the column wise striding and doing the cast for the whole list as opposed to on each of the rows. So you can see the performance benefits are there. S3 for the actual problem in question, time wise wasn't as good, but memory wise it's a big improvement because we're only considering the lists that don't have that zero in their product, so we're doing it for a smaller subset. However, the actual filter in itself is not worth it for the number of args 13. However, if I change this to look at 50, And you can see here that S3 is actually much better. So because we're looking at larger groups, there's more chance then that a zero is going to be in the group, so it can filter out even more of the groups, in which case the performance does become worth it at that stage. But that's everything for problem 8 of the Project Euler problem set. So yeah, please leave your solutions in the comments, and thanks for watching.